Any other questions before we begin with class today? Yep, my office hours will still be Tuesdays and Thursdays and Mondays. And of course, so the final is going to be, it's determined by the final schedule. So I think it's 8 a.m. on the 19th. Our last class is the 16th on Monday. So it's a Thursday, right? 16, 17, 18, 19. Yeah, I think it's a Thursday. 19th at 8 a.m. But once again, you can check that directly. Yeah, I'd say the revised midterm is due on the 17th. And yeah, honestly, my schedule is getting more free. So if my office hours don't work for you, just send me an email and I'll find a different thing. I could probably meet at the same time on Wednesday morning for like office hours as well or something like that. I'd be happy to. So, but there's no class on Wednesday, that's true. But I've got no issue showing up at 9:20 on Wednesday for office hours as well. Okay, so does that kind of clarify some things about this upcoming finals week? Excellent. Okay. So today I want to finish up equivalence relations and move on to combinatorics. So finish 9.5 and move on to chapter 6. Okay. First of all, let's, so the thing that I wasn't able to prove, but I was able to discuss last time was some sort of equivalence between equivalence relations. So an equivalence relation R on a set A. Can someone remind me what it means to have an equivalence relation R on a set A? Yes, so R is a subset of A cross A such that it is reflexive, transitive, and symmetric. Exactly. Reflexive, transitive, and symmetric. And last time I defined for you, if I have an equivalence relation, I can define the equivalence class of an element, right? I can consider the equivalence class of A, which, does anyone remember the definition of this thing? Equivalence class of A. What's that? That's the correct way to think about it, but there is a formal definition for it. Oh, wait. So we should have a set builder notation for this, right? So it certainly should be some collection of S in A such that something holds. Yeah, exactly. I will write it the other way around, but by symmetry, it doesn't matter, right? It's the collection of all S such that A comma S is inside our relation R. So it's the reverse of the notation that you gave, Morgan, but by symmetry, they're equivalent. But you do have to like pick one and then work with it, right? Like when I did that proof last time about several things being equivalent, I always started off with like A comma S and B comma S, and then used the symmetric property on one so that I had A comma S and then S comma B and whatever. Okay, I don't want to dwell on that too much, but yeah, either definition is correct, but you do have to pick one and then use symmetry. Okay, on the other hand, at the very end of the last class, I described what a partition on a set is. So what's a partition on a set? Or partition of a set, really, is the correct way to say it. I suppose it's okay if y'all don't remember and I can remind you. I mean, it's kind of exactly what it sounds like. A partition is a way of dividing up the set A into disjoint subsets. So it's a collection. This collection just has some index I. This doesn't need to be a finite number of sets or even a countable number of sets. This could be a very infinite collection of sets, AI, such that, first of all, none of the AI are empty. So all of these sets contain at least one element of A. The union of the AI is equal to the set A, and AI intersect AJ is equal to the empty set for I not equal to J. So the picture that I have for a partition, and this is not a great picture because it only has finitely many sets AI, so things can be worse, but here's like some partition of a set, say. If the points inside here are the elements of the set, and this is A1, A2, A3, A4, A5, this is a reasonable picture for a partition. I'm dividing up all the elements of the set A into bins such that no element is inside more than one bin. Each bin has exactly, or has at least one element, and yeah, they don't intersect. So this is kind of a reasonable picture for what it means to partition a set. Thank you. Any questions? Anyone have some point of these definitions that they want to discuss or ask me about? Okay, so what I want to prove now, the theorem, good. The theorem is that these are equivalent ideas in the following precise sense. From an equivalence relation, R on A, we may produce a partition and vice versa. So in a certain sense, the data of an equivalence relation is the same as the data of a partition. And the way that we produce the sets of the partition from an equivalence relation is the following. The sets AI of the partition are the equivalence classes A for A in A. Okay, so let's prove this. Let's first show the forward direction, that is, an equivalence relation gives a partition. So what I'm trying to claim now is that if I consider the collection of equivalence classes, they indeed form a partition. So we must check that equivalence classes A for all A in A form a partition. Okay. So we need to check 3 things. The first is we need to check that none of these equivalence classes are empty. My claim, so A is not empty. Why is the equivalence class of A not empty? Yeah, it contains at least A, exactly, by reflexivity. By reflexivity, the equivalence class A, the element A is inside the equivalence class of A, since A comma A is inside our relation, right? Because my equivalence class is reflexive, I must have the element A living inside the equivalence class of A. Okay, so we used one of our defining properties of an equivalence relation to show that these are non-empty. The second thing that I want to show is that the union of the AI is equal to A. So it's clear that the union over all A in A of the A, this is the equivalence classes of A, this is certainly a subset of A because it's a union of subsets of A, right? Each equivalence class is a subset of A. So if I take a big union over subsets of A, it's going to live in A, right? It is clear. Do we agree with this statement that I made? Remember, if I'm trying to show an equality of sets, I'm going to show a double inclusion. So I claim that this inclusion is clear because each of these equivalence classes are subsets of A. So if I take a union of subsets of A, it's going to be contained in A. Perfect. Now we show the other direction. We must show that A is contained inside the union of all A in A of the equivalence classes A. So want to show. Let B be an element inside A. I claim that I can find an equivalence class such that B is contained inside that equivalence class. What should that be? What is an equivalence class that B is inside of? Or more particularly, what is the name, what is a name for an equivalence class that B is inside of? Exactly, the equivalence class of B. Then B is inside the equivalence class of B, so B is an element of this union, where here we're taking all A and taking their equivalence classes. Because B is inside an equivalence class, namely the one which can be named by B, the one which has B as a representative. Is this okay? Excellent. The last point is I need to show that if the equivalence class of A is not equal to the equivalence class of B, then A intersect B is equal to the empty set. So the point here, it's not the case that all elements have their own equivalence class. The point is that this could be over counting by a ton. I'll do an example here, basically, with the integers that will kind of see what's going on. So the point is that there are many names that you can give to one equivalence class. And so the equivalence class B could be the same as the equivalence class of a lot of other elements. You can name an equivalence class by a lot of different names, or in other words, you can give an equivalence class the name of any representative inside it. So in other words, let me just do a quick aside here. Let's say we're doing the equivalence class mod 5 on Z. Well, the equivalence class of 0 is equal to the equivalence class of 5, which is equal to the equivalence class of 10, which is equal to, right? A ton of equivalence classes are equal. In this argument, I'm just saying, why is 125 inside this union? Well, 125 is inside the equivalence class of 125. But that happens to be equal to a lot of other classes. Does that kind of help what I'm doing here? Now, of course, there is the relation where everything is only related to itself. That's an equivalence relation, and then all the equivalence classes only consist of one element. But this argument works for an arbitrary equivalence relation. The point is, equivalence classes have many names. They have as many names as they have representatives. Yeah. Okay. This follows from the lemma that I proved yesterday. This follows since, according to the lemma I proved yesterday, A being equal to B is equivalent to A intersecting B not being empty. This is part of the lemma that I proved yesterday when I proved that 3 conditions were equal. And if you negate one of these conditions, then you negate the other. So if 2 equivalence classes are not equal, then they can't intersect. That follows from the negation of this if and only if statement, that the equivalence class of A is equal to the equivalence class of B, if and only if their intersection is not empty. So in other words, for any equivalence relation, we can form a partition. And now let me kind of do an example, which I already kind of described, but here's the picture that I have in mind. So I have an equivalence relation, mod 5 on Z, on the integers. So essentially, we remember that this is the relation that A comma B is inside R, inside my relation, if A is congruent to B mod 5, right? So this is some relation. This depends on tuples of elements, pairs of elements. But the map that sends A to the equivalence class of A, I mean, we can kind of examine what's going on here. For instance, 0 is sent to the equivalence class of 0, 1 is sent to the equivalence class of 1, 2 is sent to the equivalence class of 2, 3 is sent to the equivalence class of 3, 4 is sent to the equivalence class of 4, 5 is sent to the equivalence class of 5, but what is another name for the equivalence class of 5? Yeah, it's the same as the equivalence class of 0. It's the same as the equivalence class of -5, right? There's a huge number of things this is equivalent to. So really, what's the right way to picture this? The bins that I'm putting things in are remainders modulo 5. So in here, this is the class. So this has 0, 5, 10, 15, -5, -10, etc. So here are all the things that have remainder 0 modulo 5. And this subset has many names, right? I can call this the equivalence class of 0 or the equivalence class of 125 or the equivalence class of 1,000,000, right? All these are equally good names for this equivalence class, for this subset of the integers. Similarly, over here, I have 1, 6, 11, 16, -4, -9, right? This is the equivalence class of things that are congruent to 1 modulo 5. So I'm partitioning up the integers based on what their remainder is when you divide by 5. I have, and of course, there are many names for this, right? This also goes by the name of 1,000,001. It's the same equivalence class. I'm just picking different representatives or different names. Here will be all the things that are congruent to 2 modulo 5, so like 2, 7, 12, 17, etc., -3. One name for this is the equivalence class of 2, but there are many other names. Here are things like 3, 8, 13, etc. Here's like 4, -1, 9, 14, stuff like that. This is the equivalence class of 4, but it also has many names. Does this help our example about passing from elements of our set Z to equivalence classes? And notice here that my expression, the union over all A of the equivalence class of A, this is like a huge overcounting, right? Because this is equal to the equivalence class of 0, union, equivalence class of 1, union, equivalence class of 2, union, equivalence class of 3, all the way on both directions, right? This is a big union parameterized by the integers. But the point is, what's the union of the equivalence class of 0 and the equivalence class of 5? Yeah, these are the same set. And if I union a set with itself, I just get that same set back. So when I write an expression like this, it's probably a massive over-parameterization or over-counting of the unions that I require. But this is also equal to 0, union 1, union 2, union 3, union 4. This is a much reduced way of counting up all the unions. But these two expressions are equal, right? So you see why I was working with expressions like this. Does this kind of help? Excellent. I'm happy to hear it. Let me do a slightly different example that is a little more challenging. Well, it displays something a little different. Remember, I put a relation R on the real numbers R such that A comma B is inside R. No, not that R. Inside my relation R if A minus B is an integer. My question here is, how many equivalence classes do we have? Just one equivalence class? This is on R. If I only had one equivalence class, that would mean that 1 and pi are in the same equivalence class. Yes, so Val, you're correct. There are infinitely many. And now my next question to you is, are there countably many or uncountably many? Yeah, there are uncountably many equivalence classes. In fact, there's going to be one equivalence class for each number p inside the partially open interval 0 to 1, right? This is kind of the picture that I have. Here's the number line. Here's 0. Here's 1. And the idea is, once again, I think of having a comb where all of the teeth of the comb are an integer apart. And then I think of the ways that I can move the comb around such that it hits the same numbers. So one equivalence class is when I line up one of the tines of the cone. Yeah, sure. So one equivalence class is the integers. So the equivalence class of 0, what's in here? Well, 0, 1, 2, 3, and -1, right? These are all the things that the tines of the cone land on when I line up one of the tines of the cone with 0. These are all the things that are an integer away from 0. On the other hand, I can consider the equivalence class of pi. So pi I'm going to think of as 3.14159 with some repeating decimal, okay? Yeah, the size of each equivalence class is countable. It's parameterized by z, yes. So the things that are inside the equivalence class of pi are 0.141 repeating, 1.141 repeating, 2.141 repeating. If I subtract 1 from this, I get something that looks ugly, but like 1 minus 0.141 repeating, right? These are the things that are inside the equivalence class of pi. This is what happens. So here's 1, 2, 3. Here's pi. If I line up the tines of my integer comb such that one of the tines hits pi, I'm going to look at all the other things that are hit when the cone, yeah, okay, not repeating decimals, just it's an extended, it's a decimal expansion that doesn't terminate and doesn't repeat, right? So I'm going to hit all of these things that are an integer away from pi. And indeed, I find that I have some representative in between 0 and 1, right? This thing right here. This is pi minus 3. Actually, this is the better way to write everything. Pi minus 3, pi minus 2, pi minus 1, pi plus 1, right? These are the elements inside the equivalence class of pi. I should not have messed around with decimal expansions. So everything has a representative inside this interval between 0 and 1, right? No matter how you slide the cone, one of the tines will land inside this set. So I can always pick a representative inside this interval, partially closed interval. I don't close the other side because the equivalence class of 1 is the same as the equivalence class of 0. So how's that? Great. Does anyone have any further questions about this process? When I was taking physics in high school, we had a physics professor, a teacher, who would give us extra points on our homework if we said things right in class, especially if we said things that were right but annoying. So who told me that there are no repeating decimals in pi? You get points for being annoying and correct. Okay. It's the best kind of correct. So the other thing that we want to do is we want to go in the other direction. So we want to show. No, I'm very glad it was typed. It's a good point. I'm happy about it. Okay, so we want to show that a partition induces an equivalence relation. Okay, so the idea here is that from a partition, AI of A, so maybe I'll write this as a collection of sets AI indexed by I. From a partition AI of A, we produce an equivalence relation R as a subset of A cross A, where I say A comma B is inside my relation if A and B are both inside AI for some I. Did we prove the last point if A is not equal to B, then A union B? So that was with intersections. So I didn't fully prove this, but this follows from the lemma that I proved last time. Remember when I showed that 3 conditions were equivalent? That will imply this. This is one direction of the negation of that statement that I had last time. Right, this statement is true. The equivalence class A is equal to the equivalence class of B if and only if their intersection is not empty. But this implies that if they're not equal, then their intersection must be empty. So, okay. Okay, so I'm trying to build an equivalence relation from a partition. So the first thing that I need to check is that this equivalence relation, or this relation that I define this way, is reflexive. Why is this relation that I define using a partition reflexive? Well, since the union of the AI is equal to A, for any B inside A, we must have B inside some AI. So this is my notation for a collection of sets. So this is a set consisting of sets. So for instance, this is like, yeah, it's just some notation. Okay, so if B, yeah, this is how I say I have a bunch of sets that are indexed by some indexing set I. We don't need to get too much into that, unless there's confusion. Okay, but in any case, one of our assumptions on a partition is that the union of these sets AI is equal to A. So for any element B inside A, B is inside the union. But what does it mean to be inside the union? It means B is inside one of the AI. Okay, so if B is inside one of the AI, now B comma B is inside my relation because B and B are both inside AI, right? So do we agree that this is reflexive? Also, these proofs that I'm writing now are a little sketchy just in the hopes of time, and I'm not writing full sentences. I hope that you're not learning from my example. I'm just trying to finish this section. We must have B inside AI. So maybe I should write this out carefully. Then B comma B is inside the relation since B is in AI and B is in AI. Okay, so the relation is reflexive. Now I want to check that it's symmetric. So let A comma B inside R. So A is inside AI and B is inside AI for some I. Then B is inside AI and A is inside AI. So B, A is inside R. So it's symmetric. And then lastly, I mean, transitivity is going to be just also easy. So transitivity, let A comma B be inside R and B comma C inside R. So A and B are inside AI and B, C are inside AJ. However, by our definition of partition, if I is not equal to J, AI intersect AJ is equal to the empty set. And since B is inside AI and B is inside AJ, what do I conclude about I and J? Yeah, I is equal to J. So in other words, thus AI is equal to AJ. So A comma B comma C are all inside AI, and so A comma C is inside my relation because I found one set where A and C are in there together. So in this way, I produce an equivalence relation from a partition by just saying everything inside the same bucket, namely the same AI, is equivalent. How's that? I'll put a little box. How's that? Happy to hear it. Thank you. Okay, so that's pretty much all that I want to say about equivalence relations, I think. I did some examples, so it's not like you don't have any examples to work with. I would do more examples, but I do kind of want to get to counting. I don't want to only have 2 days for counting. So any questions before I start talking about combinatorics? Okay, great. Good work on equivalence relations, y'all. It's a cool topic. We had fun. Okay, chapter 6, combinatorics. All right, so here we're gonna learn how to count stuff. I'm gonna count stuff good. Learn how to count good. Okay. Here is the product rule in combinatorics. Suppose a procedure can be broken into k tasks. If there are ni ways to complete the ith task, there are n1 times n2 all the way times nk ways to complete the procedure. Okay, so that's a pretty reasonable sort of thing, right? So for instance, the first example of this is, let's say that you have, so my procedure is getting dressed. And let's say I have 10 shirts, I have 10 shirts, and I have probably like 6 pairs of pants. No, I have like 7 pairs of pants. How many ways can I get dressed? So we're breaking this up into 2 tasks, namely one task, putting on a shirt, and another task, putting on a pair of pants. And there are 10 ways that I can put on a shirt. So 10 ways of completing the first task. And then I have 7 ways of completing the second task. So I have 10 times 7, which is equal to 70. Val, are you happy with the 70 rather than 140? Is that okay? But see, I'm not counting the order in which I clothe myself. I'm just saying how many outfits do I have. In this case, order doesn't matter, right? Here I'm counting outfits. So in our later chapters, we will, order will matter, but here for the procedure of putting on an outfit, order does not matter. Okay, great. So this was when we had 2 tasks. Okay, yes, the procedure is more complicated, I understand. Here's another example, more mathy. Yes, you make good points. How many bit strings are there of length 9? And here a bit string means 9 digits that are either ones or zeros in order. So like here's a bit string 0, 1, 0, 0, 1. This is a bit string of length 5. And so I think of this as having 5 slots, and in each slot I choose either a 0 or a 1, right? So if I want to find the number of bit strings of length 9, then I think of myself as having 9 tasks, and I line them up in a row, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 tasks. And first I pick a 0 or a 1, so I have 2 choices, and I have 2 choices for each task. And so of course the answer is going to be 2 times 2 times 2, 9 times. Or in other words, 2 to the 9th. I have no idea if that's equal to 512. I believe that you're right because I have faith in my students. But I'll leave it as 2 to the 9th because then I know that I'm not wrong. So there are 2 to the 9th ways, 2 to the 9th bit strings of length 9. Is that okay? I think that this is much more concrete and much more familiar than all the things that we were just doing with partitions and equivalence relations. But any questions on these two examples? Let's do, I wish I had 5 minutes instead of 2 more minutes because I'd do 2 more examples. So here's another example. How many subsets of a finite set S, where let's say the cardinality of S is equal to N? Well, I claim I can actually count this in the exact same way that I counted bit strings, because I can put all of my elements of S in a line. Since it's a finite set, I can count them. So S1, S2, S3, all the way up to Sn. And then I'm going to associate to a subset a bit string, where I put a 0 if I include that element, and I put, no, a 0 is I don't include that element, and a 1 is I include that element. So the bit string 1, 1, 1, 1, 1, a bunch of ones, means S as a subset of S, and the bit string 0, 0, 0, 0, 0, 0, a bunch of zeros, means the empty set as a subset of S, because I haven't taken any of the elements into my subset. So of course the answer once again is 2 to the n, or 2 to the size of S, because all that I'm doing is saying the number of subsets is the same as the number of bit strings of length n. So the number of subsets of a finite set is the same as the number of bit strings of length size of S. So that's cool. We can count all sorts of things with the product rule. And it is 10:10. So how is 0, 0, 0? So the point is, here's the bijection between a subset and a bit string. So a bit string will correspond to a subset so if a 1 appears in the ith place, Si is inside my subset B. So everywhere that a 1 appears, that element appears inside my subset. 0, 0, 0, 0, 0 everywhere means S1's not in my subset, S2's not in my subset, S3's not in my subset. Actually, none of the elements of S are inside my subset. What is the subset of a set that contains none of its elements? The empty set. Right? The set corresponding to S2, the set containing the element S2 as a subset of S is the bit string 0, 1, zeros, and then zeros. The set containing S2 and S5 as a subset of S is the bit string 0, 1, 0, 0, 1, and then a bunch of zeros. The point is you can denote a subset in this case by lining up your elements and determining at each step whether or not the ith element is inside your subset. Does that help? Does that make things a little more clear? Cool. Okay. I have office hours tomorrow. And also, if my office hours don't work for y'all, send me an email. And have a nice Wednesday. This is our last Wednesday. our last Wednesday together. Have a nice Wednesday. The final is according to the final schedule, so this can be looked up, but in particular, I think it's at 8 a.m. on November 19th, but you should check that against the university calendar. I mean, probably.